In the first example here, we are going to simplify some statements using our logical equivalence table. This first statement here is A times A plus B. We could of course write that as A and A or B. So the A in front of the brackets means A dot, where the dot means the AND operator. So we could write it like this. So we just have two different notations. We can use the distributive law to distribute A inside the brackets. So we can write this as A dot A plus A dot B, which can also be written as A and A or A and B. So here is the distributive law which we proved in the previous video. Now what about A and A? Well, if we see two propositions coming together, it usually means that we can use one of these equivalences to simplify it. So A and A is shown up here, but it's actually P and P here. This is an example of one of the idempotent laws. P and P is equivalent to P. So A and A is equivalent to A. So we have A or A and B. We can now use an absorption law to deal with this here. This is the second absorption law here. P, R, P and Q. That's what we have here. We have A, R, A and B. It has the same form. See, we must have the same proposition here, P, as here, just inside the bracket. P, R, P and Q. Here A takes the place of P. A is P. So we have A, R, A and B. And we're given that this is equivalent to P. So this here must be equivalent to A. Again, this only works if this proposition and this proposition are the same. Another way to look at it when we use this notation is to work as if we are dealing with ordinary algebra. So if we have something outside a bracket, we can use the distributive law for arithmetic or algebra. We multiply A into the two terms inside the brackets. Of course, there are some differences. A dot A is not A squared. A dot A is A. That comes from the idempotent law. P and P is equivalent to P. So there are some differences. However, we can factorize just like we can in ordinary algebra. We can factorize A out of this expression here, and then we're left with 1 plus B inside the brackets. A times 1 is A times B is AB. Now, 1 plus B is actually equivalent to 1. So here we depart from ordinary algebra. Where does this come from? Well, this is 1 or B. The plus is or, of course. So, and the 1 means true. We can replace the 1 with T. So we get this domination law here. PRT is equivalent to T. So the P is the B in this case, and the T is 1, of course. So B or 1 is 1. If we take 1 and combine it with another proposition using the OR operator, we just get 1. Then we have A dot 1, that's A and 1. Well, this bit behaves just like ordinary algebra. A times 1 is A. If we go over here, P and T is just P. So this is the law that we're using, this identity law. So we have A and T. So doing it this way, using this notation, we didn't actually have to use the absorption law because we did some factorizing. We factorized A out of these two terms. Let's look at this one, A and not A or B. Now I will just stick with this notation here. We can multiply the A into the brackets just like in ordinary algebra. So we get A dot A bar and we have A dot B. Now A dot A bar, we looked that up. If we see two propositions, if we see the same proposition combined with itself, it's probably in this table. So in some ways, so we have A and its negation. So if we go down here, we see the complement laws. We see P and its negation is equivalent to false or zero. So we can replace this inside the brackets with, sorry, we can replace A dot A bar with 0. So now we have 0 or AB. Now if we look this up, it's one of the identity laws. P or 0 is equivalent to P. So that's what we're applying here, where P in this case is AB. So AB or 0 is just AB. This just behaves like ordinary algebra. If we add 0 onto a number, we don't change the number. In this example here, we want A plus the negation of AB. We can use one of De Morgan's laws to break this term into two terms. So we go over here, we see that the negation of P dot Q is equivalent to the, not P or not Q. So the not AB is equivalent to not A plus not B. Now we've A plus not A. So that looks like one of the complement law, because A, we can think of not A as the complement of A. Just like in set theory, you know, A and A complement are disjoint sets. Well, A and A bar are disjoint operators, if you like. So we have over here P or not P is equivalent to T, which is or 1. Same situation here. Instead of P we've A or not A is equivalent to 1. Now we've seen this before. Adding 1 onto a proposition just gives us 1. This is the domination law. P or 1 is equivalent to 1. So here P is just not B. The fact that A or not A and B is equivalent to 1 means that this statement is a tautology. Demonstrate that not P and P or Q implies Q is a tautology. So rather than making out a truth table, we're going to use this table of equivalences. We could do it using a truth table, of course. Now, we have not P and P or Q. We can take not P into the brackets, distribute it in. That's one of the distributive laws, just like in algebra. Now we've not P and P. So that looks, we have two similar looking propositions coming together. So we see that it's the second complement law. P and not P is equivalent to false, which is 0. False or this proposition is just this proposition, not P and Q. So it's like adding 0 onto a number in ordinary algebra. It's one of the identity laws, this one here, P plus 0 is equivalent to P. Now, the next thing we use is the material implication law. We have this proposition here on the left hand side, not P and Q, implying Q. So we can see that we have one proposition implying another proposition that's equivalent to the negation of the first proposition or the second proposition. So here it's P bar plus Q. So we take the negation of this here and plus it with this proposition. So this left hand side is the P in this table and the right hand side is Q. Well, P is not equal to this, of course, but I'm just comparing it with this. So what do? Well, we take the proposition on the left hand side and negate it. So we have to negate this proposition here. We negate this. So we put a bar over this. So we put a bar over P bar dot Q. And what do we do with this the negation of this proposition? We add the proposition on the right hand side. See this? We're just following this here. We just replace the p here with p bar dot q, and the q, well, we replace it with q. That's the same. So we get the negation of p bar dot q, and we add q onto it. Now we have the negation of a product of propositions. So that looks like one of De Morgan's laws. The negation of p dot q is the negation of p plus the negation of q. So we can write this product p bar dot q as a sum. We just take the negation over each factor in the product. So we have the negation of p plus the negation of q. That's exactly what we do when we use De Morgan's law. Now, the negation of a proposition is just the proposition itself. It's called a double negation. We have that up here. Not p is just equivalent to p. Now we have three propositions added together. We can use the associative law to move these brackets. It's not actually mentioned here, but it's implied here. So here's the associate operator for combining three propositions using the OR operator. P or Q or R is equivalent to P or Q or R. So it doesn't matter where we put the brackets. So what we do here is we shift the brackets so that this is equivalent to P plus Q bar plus Q. So we have two similar looking propositions coming together here, not Q and Q. So we see that as one of the complement laws. P or not P is equivalent to 1. So we've that scenario here, Q or not Q is equivalent to 1. So we end up at P plus 1, P or 1. So we go up to this domination law and see that P or 1 is equivalent to 1. The fact that we get 1 at the end shows that this statement is a tautology. For this first statement, we want to show that not A and B and C is equivalent to not A or not B or not C. The associative laws assure us that we can combine three propositions taking any two at a time, where the operator is the AND operator. So P and Q taken first, then AND OR is equivalent to taking Q and R first and then getting P and the result, just like ordinary multiplication. So we can take any of these two at a time because we're just dealing with the AND operator here. So let's take A and B. So A and B is a single proposition. Now we can apply De Morgan's law to this. That is, not P and Q is equivalent to not P or not Q. So this is equivalent to, I'll just write an equal sign. I won't keep writing the equivalent sign. This is equivalent to not A dot B or not C. So I'm just applying De Morgan's law where P is A dot B and Q is C. Now, of course, we can apply De Morgan's law to this here. So not A dot B is equivalent to not A or not B. And of course we have this, so that's what we had to show. Now in this second example, we can start by using the distributive law. So for this distributive law, we have P dot Q plus R is equivalent to P dot Q plus P dot R, just like in ordinary algebra. We can take the A and multiply it into the terms in the brackets. Now, when I combine A with A dot C bar, we have three propositions, and the operator is just the AND operator, so we can take any two at a time. So what we do is we take these two together and replace this using one of the laws. It's the idempotent law actually. P and P is equivalent to P, so A and A is equivalent to A. Finally, we can use the distributive law in reverse to write this here as A and B are not C. Here we want to show that not P and Q are R and not Q or P and not R is equivalent to not Q. Now we can actually multiply this out just like in ordinary algebra. So we're just applying the distributive law. It's actually the second distributive law here. P and Q are R. We can take the P and multiply it, if you like, inside the brackets. Actually, this is just an extension of the distributive law, where we start off with by applying R into both of these, and then we can actually apply P, not PQ, into both brackets. So the distributive law can be extended to this situation, where we have more than one term. We don't just have R into this bracket, but we have not PQ into this bracket as well. So we have a dot here. The dot represents and. Anyway, so what I've done is I've actually taken this term and worked it through this bracket here. So not PQ times not Q plus not PQ times P times not R, and then I've taken R and multiplied it into these two terms, so we get 4 terms in total. Now I'm applying De Morgan's laws here. Not P and Q is equivalent to not P or not Q. Here we have it, not P and Q is equivalent to not P or not Q. So I've applied it twice here, here and here. On this next line here, I've used the distributive law to take Q bar into this bracket and to take P R bar into this bracket here. So we have P bar dot Q bar. Now Q bar dot itself, Q bar dot Q bar is just Q bar. So I'm just using the idempotent law here. P and itself is equivalent to just P. So Q bar and Q bar is just Q bar. Similarly, well, not similarly, over here we have PR bar dot P bar. So that's P bar dot P dot R bar. So we could take, using the associative law, we can take P bar dot P first. So we can use a complement law here. P dot P bar is equivalent to 0. So when I multiply PR by P bar, we get from the P dot P bar, we get 0 here. And with dot 0 with R bar. Then we have PR bar dot Q bar. Can't do anything with that. And I've just written out our Q bar here. Over here, we get a 0 because we can use the commutative law to write R dot P dot R bar as R dot R bar dot P. So we apply the commutative law to P dot R bar, which tells us the order doesn't matter. P dot Q is equivalent to Q dot P. So we can switch the order of the P and the R bar. And then we have an R dot R bar situation. So we can use the complement law to replace R dot R bar with 0. Now 0 dot of any proposition is 0. That's one of the domination laws. P dot 0 is equivalent to 0. So these are just zeros. So, and if we take anything and add 0 onto it, it doesn't change it. That's actually an identity law. P plus 0 is equivalent to P. So adding 0, so we can just take out the zeros. That's a 0 as well. We can just drop out the zeros. So now we're left at this, just these 4 terms. And what I did then was factorized Q bar out of these 4 terms. So this is a case of using the distributive law in reverse. So the distributive law here is applied, the associative law. The associative law says that if we're adding several propositions together, it doesn't matter which way we add them. Actually, we are using the distributive law. We can take Q bar out of the 4 terms. You see here, P dot Q plus P dot R is the same as P dot Q plus R. So we can take the P out of these two. And we can extend this to more than 2 terms. So we actually have 1, 2, 3, 4 terms here. We can factorize Q bar out, just like in ordinary algebra. So notice when we take the Q bar out of this expression, we will be left with a 1 here. Q bar dot 1 is just Q bar. So that works like ordinary algebra. That's one of the identity laws. P dot 1 is equivalent to P. So Q bar dot 1 is equivalent to Q bar. Now, the last step uses a domination law. If we take any proposition P and add 1 to it, we find that P plus 1 is equivalent to 1. Now, of course, it looks more complicated here, but it doesn't matter. We can think of the P bar plus the PR bar plus the R as our single proposition. So basically we have, once we're adding 1 onto a proposition, we get 1. So that's what's done in the domination law. We add 1 onto any proposition. So the P bar plus PR bar plus R takes the place of the P in this domination law. Add 1, we just get 1. And finally we're left with Q bar dot 1, which is Q bar. That's this identity law here. Part 4, we want to show that x dot y implies x bar dot y plus y bar is logically equivalent to x bar plus y bar. So the first step I've used here is material implication. P implies Q is equivalent to not P plus Q. So xy takes the place of P, so we've not P, so we've not xy, plus the right hand side. The right hand side takes the place of Q. So P is xy and Q is x bar y plus y bar. The next step I've used is one of De Morgan's laws. Not P dot Q is equivalent to not P plus not Q. So not x dot y is equivalent to not x plus not y. Then I've used one of the distributive laws. We can factorize x bar out of x bar plus x bar y to get x bar dot 1 plus y bar. Then we can use a domination law to replace 1 plus y with just 1. P plus 1 is equivalent to 1. X bar dot 1 is x bar. That's the identity law. So we're left with x bar plus y bar, which is what we have to show. In this example, we want to show that A implies B plus not A not B is equivalent to not A plus B. So we have an implication in this statement, so we can use material implication. So P takes the place of A, and Q is B plus not A times not B. So P implies Q is equivalent to not P plus Q. So we take not P, so it's not A, plus the right hand side. And then I've applied one of De Morgan's laws to not A dot not B. So we just take not A plus not B. Double negation appears here. Not B is just B. B or B is B. That's the idempotent law here. P plus P is equivalent to P. Now let's look at the truth table. So we've two propositions A and B. So for B I've written 0, 1, 0, 1. We just alternate in steps of 1. Then for A we alternate in steps of 2. So we have 0, 0, 1, 1, giving us 4 rows. A bar is part of this statement. So I have a column here for A bar, so we just flip the values of A. A bar plus B is done here. We need A bar plus B. So we have a 1 if either of the values of B or A bar is a 1. Otherwise we have a 0 here because both of these are 0. We need B bar, that's coming into this. So we flip the values of B, so we get 1, 0, 1, 0. We need A dot B bar, that's part of it. So that's A and B bar. So that's only true when both A and B bar are true. So that happens in the third row when A is 1, and when B bar is 1, then A B bar is 1. Zeros elsewhere. Then we want to negate A B bar. We want A B bar bar, so we flip the values here. So the two zeros become 1s, 1 becomes 0, 0 becomes 1. Finally, we can now get B plus A B bar bar. So we have 0 or 1. This should actually be a 1. So here B is 1, AB bar bar is 1, so this is going to be 1. We have a 0 here and a 0 here, so we have a 0 here. This is 1, this is 1, so we have a 1 here. Now finally, we can look at A implies B plus AB bar bar. So we have a 0 here, a 1 here. That means we have a 1 here. Remember, if A is false, then the implication operator yields a true value. A is 0 here, so the implication operator yields a true value. Now, A is true here, but B plus AB bar bar is false. So true. So if A is true and if we have a 0 here, the implication operator yields 0. So that's the only exception. So that's the 1, 0, 0 thing I mentioned in previous videos. Finally, A is 1. This is 1. So this A is true. This proposition is true. So the implication is true. Notice now that this column is identical to A bar plus B. So these two columns are the same, showing the equivalence.